All right, so today I'm gonna be explaining another important paper with the title Generative Modeling by Estimating Gradients of the Data Distribution. This paper in NeurIPS 2019. We introduce a new generative model where samples are produced via Langevin dynamics using the gradients of the data distribution estimated via score matching. I have a playlist about score matching that I talk about the original paper in 2005, and so because gradients can be ill-defined and hard to estimate when the data resides on low-dimensional manifolds, we perturb the data with different levels of Gaussian noise. And this was the motivation for those denoising version of score matching. The original idea of score matching is that instead of P, we are learning gradient of P. So P, the likelihood is implicit because we are learning only the gradient of that to match the target gradient. And when you want to sample it after you have learned the score, when you want to sample it, if you use Langevin dynamics, it has many problems. But that's why we need annealed version of Langevin dynamics, where we use gradients corresponding to gradually decreasing noise levels. It looks like diffusion that gradually you change or in some versions of diffusion, some people use scheduling. But this paper is only about score matching. You can connect it to the idea of diffusion, but the idea is just denoising score matching, making it more efficient. And this score matching, 90%, 95% of papers about score matching is about continuous data, like images, because the gradient makes sense. For discrete data, you need to do many relaxations. You need to use Gumbel softmax, many problems, even defining the gradient. So, for example, today we call it concrete score matching, which is good for discrete score matching. So let's carry on this score matching for score estimation. We repurpose it for score matching. Using score matching, we can directly train a score network as theta to estimate the gradient of your probability distribution of data without training model to estimate P data first. Different from typical usage of score matching, we opt not to use gradient of energy-based model as the score network to avoid extra computation due to higher order gradients. The objective minimizes this expectation, which, it is not written here, but Havarian in 2005 showed that you can easily write it like this. Trace of the gradient plus half of the norm of the F theta. So denoising score matching is I think this reference 61 is in 2011. 6 years after 2005, which Havarian introduced. In this paper, I think Vincent was the author of this paper, 2011, that he talked about how denoising score matching, after he proved many things about explicit score matching, implicit score matching, then he proved the denoising score matching, which is just a variant of score matching that completely circumvents the trace. It first perturbs the data point with a pre-specified noise distribution and then employs score matching to estimate the score of the perturbed data distribution. The objective was proved equivalent to the following. So it was proved equivalent to the following. And the optimal score network satisfies this when this is equivalent to gradient of log of Q. Now notice that X tilde here is not the data, is the noisy version of the data, noisy version of your sample. It's a perturbed, we draw it from perturbed distribution. Just like denoising autoencoder, that you put a noisy version to the autoencoder instead of just simple X, we put X tilde. Here is the same. And then the sliced version is very interesting because it uses just the random projections. These, do you see V transpose and then multiplied by V here? So this becomes a scalar, and this is a scalar. So we are projecting them because data lies in a low-dimensional manifold. So it's a trick to make it low-dimensional very fast by just a random projection, because V is just random. It's just drawing from this. You get the expectation of overall these random projections that you're. A piece of V, as I said, is just a distribution of random vectors that could be multivariate standard normal. So this term can be efficiently computed by forward mode auto-differentiation, unlike denoising score matching, which estimates the scores of the perturbed data. Sliced score matching provides score estimation for the original unperturbed data. So 3 is more natural because it's still the unperturbed data, but you have done a projection. But requires around 4 times more computation just because of this forward mode auto-differentiation. And then sampling the Langevin dynamics. Langevin dynamics can produce samples from probability and density P using only the score function. Given a fixed step size and initial value X tilde, we draw it from pi. Pi is just a prior distribution, and the Langevin dynamic method recursively computes the following. So this Z is a normal distribution. It's a noise. The distribution of X tilde equals P when epsilon goes to 0, you are reducing the amount of noise that is given, because epsilon is multiplied by the normal distribution, and you are reducing it. When epsilon is greater than 0, a Metropolis Hastings update is needed to correct the error of equation 4, but it can often be ignored in practice. In this work, we assume this error is negligible when epsilon is small and t is large. The sampling from equation 4 only requires the score function, gradient of log of p. Therefore, in order to obtain samples from p data, we can first train our score network and then approximately obtain samples from Langevin dynamics. The key idea, and this is the key idea of our framework for score-based generative modeling. On the left, you see sliced score matching, very noisy, because this is the loss when you have multiple epochs. But here, when iterations goes, as you see, it's very smooth. The training is very nice if you use denoising score matching. If you use data that are perturbed. And Here you see inaccurate score estimation with score matching. And here they talk about slow mixing of Langevin dynamics. When two modes of data distribution are separated by low density regions, Langevin dynamics will not be able to correctly recover the relative weights of these two modes in reasonable time, and therefore might not converge to the true distribution. Our analysis of this are largely inspired by this reference, which analyzed the same phenomena in the context of density estimation with score matching. So consider the mixture distribution, this mixture of P1 and P2. That P1, P2 are just normalized distribution. In either case, the score does not depend on pi. So since Langevin dynamics uses gradient of log of p data to sample from p data, the samples obtained will not depend on pi. So in practice, this analysis also holds when different modes have approximately disjoint supports. So we test Langevin dynamic sampling for the same mixture of Gaussian. And here they talk about noise conditional score networks, learning and inference. Built upon this intuition, we propose to improve the score-based generative modeling by perturbing the data using various levels of noise, simultaneously estimating scores corresponding to all noise levels by training a single conditional score network. After training when using Langevin dynamics to generate samples, we initially use scores corresponding to large noise and gradually anneal down the noise level. This simulated annealing in physics and AI, it means that it's based on physical process that gradually you reduce temperature. And same here, gradually you reduce the noise. So these sigma i's, there are positive geometric sequences that satisfy this. We choose a noise level such that sigma 1 is large enough to mitigate the difficulties that we discussed, and sigma L, the last one, is small enough to minimize the effects on data. So both sliced and denoising score matching can train NCSNs, and we adopt denoising score matching as it is slightly faster and naturally fits the task of estimating scores of noise perturbed data distribution. However, we emphasize that empirically sliced score matching can train as well as denoising score matching. So we choose the noise to be this Q. So we can so the denoising score matching is this. And we combine it to get a unified objective. But the lambdas is just a coefficient depending on sigma I. So there are many choices of lambda. Here they show the algorithm for annealed Langevin dynamics. This alpha now is designed like this. You design it because the input of the algorithm is the sigma i's from 1 to L different noise levels. So you design it and you draw just usual from random distribution, the normal distribution. And once you have learned a theta, you can always sample it very easily. So this is inception and FID scores for C4R10. And this is the in-painting with annealed Langevin dynamics. There is a bit in painting here. So after you update your X, you do this recursive estimate. Because M is just a mask to show, for example, you have a picture, some parts of that is regions that are not occluded. So these are the intermediate samples from Langevin dynamics. And this is uncurated samples of MNIST, CELAP A and CFAR 10.